So thank you so much, Dr. Kashab, Dr. Nawas, Dr. Patin, and Dr. Meta for your kind words. I want you to know that it has been an honor to work with you for the past, 1 year and a half probably now. So when Dr. Kashab, or as I like to call him, Rahul, because he's a personal friend, asked me to prepare this lecture, I really want to put some slides together that actually reflect that what you should know as a junior researcher, and not like something that you should know as a biostatistician, or someone who likes to know all the mathematical formulas for calculated mean or standard deviation stuff. So this will be very practical, as Dr. Kasha said. This will be more of the theoretical part because you don't have access to SPSS, which is the more user-friendly statistical package that I use to teach biostats. But that's all right. Um, so as far as the introduction, I want to tell you a little bit more about my journey. I actually hate biostats and hate research in the earlier part of my career when I was in med school. I didn't like it at all. But I realized that if I wanted to pursue my goal of matching into a internal medicine residency program in the US, I had to actually, get my hands on research experiences, and biostats was my way in. So I hope that you find this lecture useful. Biostats has been a huge part of my life for the past 3 to 4 years. It has opened dozens of, if not hundreds of doors for me, and I think that this is a huge part of my success at this point in my career. So the lecture today is called Biostats 101, the basics. Um, yeah, so the objective for the lecture for today will be to teach you how to dif- differentiate between different types of variables, understand what a p-value is, because I know there's a lot of confusion in there. Differentiate between descriptive statistics and inferential statistics. Those are not the same, and they can certainly be whole different perspective when you're writing your paper or when you're conducting your study. And finally, learn when to use each statistical test. Um, the outline for the lecture is basically these three main parts. The one in red is, I just put it there for completeness sake, but it is more like an epidemiological stuff, and I don't think we had the time to go over that. But if we do, we can certainly talk about those things. But the first part would be describing populations. So we need to really understand the basics, which is basically variables. I like to, call this part the most critical part of learning biostats, because if you know what are your variables, what are the types of variables, what are you collecting, what are you analyzing, then you can choose the right statistical test. If you don't know your variables, you don't know the basics, you will be probably getting lost somewhere in the future. Okay, so this is the most critical part. Then hypothesis testing. And in this part, I want to really spend few moments talking about the p-value, because I know there's a lot of myths, confusions, and you probably don't have the actual concept clear in your head. And I would like to try to make it that clear for you. And the steps for hypothesis testing, that's a really nice slide that actually provides an outline or a framework on how to actually interpret some statistical tests, so that will be useful. And the most practical part of the lecture will be the selection of a statistical test. I will talk about normality tests and all the type all the more common types of statistical tests that are available to you, and how to actually choose one from another. So let's start. Types of variable. So basically, I like to divide these as both quantitative and qualitative values. So quantitative, as the name says it all, are variables that are in numbers. Okay, so basically, quantitative variables are continuous variables. Okay, so continuous variables are things like age, height, or heart rate. Okay, we can actually measure that in terms of numbers. Some other examples are glucose levels or cholesterol levels. Okay, those are numerical things. Now, let's think for a second on qualitative variables. These are basically words, they're not numbers. So, for example, the first category will be dichotomous or binary variable. This qualitative variable actually has only two possibilities. It can be a yes or a no. For example, if you are talking about genetic mutations, you have the wild type gene and the mutant gene. Okay, just one or another. If you are conducting a case control study, you are working with cases and control. That's your variable. Okay, just only two paths. Another example would be the presence of diabetes, yes or no. Presence of hypertension, yes or no. Okay, two possibilities, dichotomous binary variables. Okay, then what happens if this becomes more than that? If you have more than two categories, you have three or four or five or whatever you may have. Like for example, the list of countries in the visual study, or for example, gender. You can be male, female, transgender, etc., or race. You can be Hispanic, or race or ethnicity. You can be Hispanic, African American, um, you know, you can be Asian, and all of these kind of different types of races. The important thing in the nominal or categorical type of variable is that they don't have an order. You cannot order them. A female cannot be more than a male, and a male cannot be more than a female. You cannot put it in a particular order or hierarchy. Okay, and that's the thing that does happen with the ordinal variable. For example, cancer stage, you can be stage 1, 2, 3, 4, but stage 4 is more severe than stage 1. Okay, you can order them, even though they are basically qualitative. There are characteristics, there are names. Okay, Apgar score is another one, and you may actually tell me like, hey, Dr. Mautong, you're crazy. Apgar score is numeric. Yeah, it's numeric, but for practical use, it is an ordinal variable because you can order the score of the Apgar by 1, 2, 3, 4, 5 until 10. Okay, it follows an order. Another good example is the New York Heart Association classification. You have NYHA 1, 2, 3, and 4. It follows an order, even though it's actually a name or a category. Okay, and that's the main difference between nominal and ordinal. Count variables are also part of the quantitative variables. It also kind of it's similar. For example, the number of RBCs that you have, the number of leukocytes, the number of glucose, etc. Well, actually not glucose, but the main difference between count and continuous variables is that count variables cannot be divided. For example, the number of children you have, or the number of titles you have, like for example, MD, masters, PhD, or whatever. You cannot I have three of them, for example. You cannot divide them. You cannot have 1.5 sons or children or daughters, for example. Okay, the number of extremities I have four extremities. I cannot divide them. I cannot have one and a half of them or two and a half of them. So that's the main difference between count variables and continuous variables. Okay, and then time to event, it's basically for when you're conducting survival analysis. Time to event, I like to think of it as a mix variable because you actually need the number of days um, from when you're start counting to when the event happens, for example, relapse or mortality. Okay, and you actually need another variable, which is a dichotomous variable, and says like relapse, yes or no. Or you need, for example, mortality or death, yes or no. You need to have that. You need to have the occurrence of the event, yes or no, and you also need to have the days until what that occurs. Okay. If you have any questions at any point, or you need further clarification, please feel free to interrupt me. Okay. We will also do a Q&A at the very last portion of this lecture, but be aware that if you feel lost for a second, please don't hesitate to interrupt me. Okay. Now that this is understood, and I hope it is, because as I already said, it's the most critical part of the lecture, and actually to understand in biostats, we can move on. Okay, so just as a recapitulation, we have qualitative and quantitative values. Quantitative, think of it as numbers. Qualitative, think of that as words and characteristics. Okay, you have dichotomous, two path, yes or no. We have nominal, um, different characteristics or categories, but not in a particular order, and ordinal characteristics that are in a particular order. Okay, sounds good. All right. So when you're describing your population, or your study population, or the particular set of data that you have, each individual or each patient or each participant is a unit of analysis. Okay, and your database is basically a list of all of these units of analysis, or patients or participants, that has different variables. Okay, so how do you describe your qualitative data? So, or your quantitative data? So that's a very good question. And when you have qualitative data, you actually use your frequency, frequency percentage. Okay, and we will see that in our slide. Yeah, in our slide. And what happens when you have your quantitative data? How you summarize it, or how you describe that? So basically, we have two huge classifications, I think, and one of it is the measures of central tendency. So the three most common ways to describe quantitative data are with the mean, which is basically an average of a set of numbers, and you basically sum all of that numbers, and add them together, and they divide by the count of values, and you get your mean, which is basically an average. We all know what a mean on an average is. Median is a little more complicated, and median is actually when you organize all your sets of of values. For example, if we have hours spent studying per week, we have all of these individuals. This is individual number 1, 2, 3, 4, and whatever. We organize them in a particular order, in an ascending order, from the minimum, from the smallest number to the largest one. Okay, and then we actually take the one in the middle. Okay, so here we have 5 numbers from the middle to here, from the start, and from the middle to the finish line, we also have 5 numbers. So when this happens, we actually have to add up this number and this number, which is 24, and we divide it by 2 to get the 12. So that's the median. But if we actually had a number in here, let's say 11, then 11 will be the median, because this is where you actually divide your data in half. So this is the lower half, and this is the upper half. And this, the median, is the exact number or value that is in the exact middle of your data. What happens is, if you don't have um, If you have a number in the middle that can divide the data, you basically have to add up the two numbers in the middle and divide it by 2. Okay. And then the mode is the value that appears more frequently, basically that the value that repeats the most. In this particular set of values, the mode is 9 because we have 3 individuals with 9 hours spent studying per week. Okay, so the mean, if we add up all of these numbers and divide it by 10, which is the count of each unit of analysis, we will have that the mean is 13.1, the mode is 9 because it's the most repeated number, and the median is basically 12 because we add up these two numbers and divide it by 2. If we have one value that divides the data in half, it will be that value. But because we don't have a value that divides them, we actually have to calculate the median. Okay, and the range is basically when you subtract the largest number or value to with the smallest number or value, and that will be 20 minus 9, 11. Okay. um, Descriptive statistics measures of variability. Sometimes these are called measures of central tendency because they actually try to summarize what happened in the middle. If you actually spend a second thinking of it, the median is basically like some sort of a statistic that's telling you like an average or something that happened in the middle of the data. The median is the same thing. It's actually the exact point where the data divides in half. The mode can be something like that too, and that's why they're called measures of central tendency. Okay, but sometimes we need to account for the variability because, as you know, if we conduct the same study repeated times, we can actually end up with different estimates. Like, for example, the first study will put that the prevalence of diabetes in Ecuador is 14%, and then we conduct another study like with the same characteristics some months later, and we can end up with prevalence of 18. Okay, so these measures of variabilities actually help you to put put some values around the mean and actually have some flexibility to have some plausible values that your mean can fit in. Okay, and so basically the range, which I was talking about previously in the previous slide, is the difference between the highest and the lowest value in the data set. The variance is actually a formula that can actually reflect the average of the square difference between each data point and the mean. And I don't like to get into the nitty-gritty details of these formulas, but I want you to focus your attention on the standard deviation and the interquartile range. So the standard deviation is the square foot of the variance representing the average distance of each data point from the mean. Okay, so if we go to this graphic, this is the mean in the center of the data. That's why it is a measure of central tendency, and this is the standard deviation. Okay, so this is basically the range of plausible values that your mean can fluctuate. And actually, there's a central limit theorem that says that one standard deviation away from the mean in the upper portion and one standard deviation away from the mean in the lower portion, it's equal to the 68% of data. Okay, and if you add two standard deviations ups and down, these would be around 95% of your data. So basically, all of your all of the data that you're collating, for example, about glucose level, the mean is, I don't know, 102. Okay, but there are there are values that fall out in the lower portion of the distribution and fall in the upper portion of your distribution. So what this basically tells you is that some value can be located either one standard deviation or two standard deviations or even three standard deviations. Okay, and these standard deviations actually account for the 68% of your data for one standard deviation and the 95% of your data in two standard deviations. So for example, I can have a value of 71. Okay, so where is this located? This will be probably located around two standard deviations from the mean, or a value of 145. Where is this located? This will be probably located here. But if you have some extreme values, let me raise this for, yeah. If you have more extreme values, like for example, I don't know, 210, these would actually fall here, even either in the three standard deviation part or even a more unlikely estimate. Okay, so this is a standard deviation. The standard deviation basically accounts for the variability of the data and actually helps you to locate where a specific point is relating to the mean. Okay, and interquartile range actually, oh, sorry. Okay, so interquartile range is actually the same, actually has the same purpose. It actually wants to locate and locate a certain value and account for the variability of the data. But one thing that I want you to go after this lecture is that the standard deviation always, always, always will be next to the mean. Okay? It will always be next to the mean. If you see a mean, you will probably see a standard deviation next to it. And interquartile range goes with the median. Okay? And why is that? It's basically because they are calculated based on these measures of central tendency. That's why we were talking about means and we were talking about standard deviations, and we are now going to talk about medians and interquartile range. Okay. Oh, another thing that I also like you to know and go and be with you after this lecture is that mean and standard deviation is used to describe normal distributed data. Okay, normal. Sorry for my horrific drawings. And interquartile range is actually used to describe non-normal data. And we will get to that in a second, but I just want you to have that in the back of your head, okay? And I will actually answer your question as why the mean and the standard deviation describes normal distributed data and why the median and interquartile range describe non-normal data, okay? We will get to that in a second. So now, the interquartile range is the range between the first quartile, or what is the same, the 25th percentile, and the third percentile, or 75th percentile. Okay, so why is it called interquartile range? Because this is the first quartile. The median, by definition, is quartile two, or percentile the 50th percentile, and Q3, or the quartile 3, is actually 75. So this is 25, this is 50, and this is 75. So the interquartile range actually is something that it's like a synonym. I like to view it as a synonym of the standard deviation, but for non-normally distributed data, because it actually serves the same purpose. Here is your median, which is your measure of central tendency, and here is the interquarter range where the values can go over. For example, if we have the same example and the median is 102, these are the other values of your other participants. For example, this patient can have, like, I don't know, 79 glucose levels, and these can have like 130 or stuff. And this is basically the same thing that happens with the standard deviation. Okay, is basically the same. But why do we use one or another? Basically, it works better when it describes non normal distributed data, the standard deviation and the mean, and the median and interquartile range works better when it describes non-normally distributed data, and we will see that in a second. All right, so to end this part of the lecture, and I will pause for a second to see if you have any questions. If you have a given type of variable, for example, continuous, which is age, height, rate, heart rate, and you want to summarize that, you want to use a measure of central tendency like the mean and the median, and you would also like to account for the variability with the standard deviation, the range, and the interquartile range, like we just saw, right? This is how you describe this type of data. And the visualization method, which we will talk in a second, will be basically histograms, box plot, and scatter plot. And we will get to that in a second. Dichotomous variables or binary, remember that these are qualitative variables. For example, wild type, mutant, talking about the genetic mutation, case and control, yes or no. You know, these are dichotomous variables, only two possibilities, and you can describe them by proportion, which is basically it's similar to percentage, because if you have, like, for example, 60% of diabetics in your population, your proportion would be 0.6. So basically it's the same but expressed in another way, okay, in decimals. And 100% would be 1, and this is how you represent this type of qualitative variables. Frequency is basically the count of, for example, if I have I don't know, 200 individuals and 100 of them have hypertension, this will be the frequency. The percentage would be 50% because it's the half of them, and the proportion will be 0.5. Okay, this 50. So this is the frequency, basically the count. The percentage is, the percentage, and the proportion is basically the same thing as the percentage, but expressed in decimals. Okay. All right. So for these, we will use a bar chart, and we will get to that in a second. And for nominal or categorical variables, which are gender, race, and so on and so on, we use the same measures or descriptive tools as the dichotomous, basically proportions, percentage, frequencies. Okay. For ordinal data, which is basically qualitative variable that has an actual order or hierarchy, we use the same as the dichotomous. Okay. For recount variables, which is basically a quantitative variables, we use the same as continuous. We use the mean, the median, standard deviation, interquartile range, and the visualization method or graphics that we can actually build are the same as continuous. And from time to event data, this goes beyond the goals of these lectures, but we can also use the same as continuous variables, and the visualization method will be a survival curve, or also called Kaplan-Meier curve. Okay. So this is the first part of the lecture. Please let me know if you understood it. We will pause for a second, and if you have any questions, this is the right time for it. you can unmute yourself or raise your hand, and I will unmute you. Let me see your faces for a second. All good? We understand this? Yeah. No questions? All right. Let's go ahead then. Just give me a second. I have a sip of water or I get a sore throat, and I don't want that. All right. So the next part of the lecture is basically the graphic representation of descriptive statistics. So these are the basic graphics that we can build independent of each type of variable. So for example, an histogram is something that we use for quantitative data. And basically it is a bar graph that represents the frequency distribution of the data set. Each bar height shows the number of data points that fall within that specific range of values. So this is an example of an histogram. So basically we have the range of ages, and we actually have here how many individuals, which are two, fall within this range of 20 to 30. And the same thing for the range from 30 to 40. We have that four individuals fall in this range. The things this actually the same thing for 40 to 50, four individuals, and for from 50 to 60, it's five individuals. So basically, this is an histogram, and we use to represent quantitative data with an histogram. Okay, a box plot is actually something that helps you display the distribution of a data set, and but showing the median, the quartiles. Remember quartile 1 and or percentile 25, quartile 3 or percentile 75, and the median, which is percentile 50 or quartile 2. And the outliers. Outliers are basically values that are so extreme that go beyond the quartiles and the minimum and maximal values, and we will see that in a second. So it basically is a box. It is basically this. This is the median. This is the quartile 3. This is quartile 2, and this is the maximum value. This is the minimum value, and here you can find some outliers. We will get to that in a second. Next slide shows a perfect picture for that. The bar chart is basically what we use to represent qualitative data, and basically is, I don't know, the percentage or the frequency of yes and no for, I don't know, diabetes, and this is a bar here, and this is another bar here. So this is like 60%, and this is like 40%. That's a bar chart. Pretty easy to understand and digest. We have probably already know what a bar chart is, and we have probably utilized at some point in our life. A pie chart is basically another way that we can actually describe in a graphical way our data, and it's basically like this. It looks like a pie, and it basically says like, this is 40% of your diet, which should be carbohydrates, and 30% that should be protein, and 30% that should be lipids or whatever. This is a pie chart. A scatter plot. A scatter plot is basically another type of graphic that actually helps you to understand what's happening when you have two continuous variables. Okay, like for example, when you're doing a correlation between uric acid levels and glucose levels, you will probably run a correlation test, and you also would like to build a scatter plot, and we will basically see that in a second. So basically, it is a graph that have some scatter plot, scatter points here and there, and actually measures how they will correlate. Okay. All right. So let's get to the examples here. So these are the examples. This is a bar chart, pretty easy to understand. You have in the x-axis all the categories. For example, I don't know, the stages of the New York Heart Association classification. You have 1, 2, 3, 4, and you have how many patients actually have, you know, classification 1 or 2 or 3, 4. This is like around 16. This is like around, I don't know, 13. This is 10, and this is 15. You can also, instead of just counting or having the frequency in the y-axis, you can actually have the percentages. Okay, that is a frequent way to represent um, qualitative data. All right. So an Instagram, basically an Instagram is what we already saw. I will not spend so much time because I already explained that in the previous slide. This is the pie chart. The pie chart is basically similar to a bar chart, but because you are representing a pie or a cake, you actually have a better visual representation of how much that particular category contribute to the whole percentage. For example, if we take into account the mortality causes for 25 to 34 years old, we will have that the most part of it will be unintentional injuries, followed by homicide and suicide, malignant neoplasm, heart disease, HIV, and all others. So we can actually, you know, see how that particular category contribute to the whole percentage. Okay, and the box plot is what I was already explaining to you in the previous slide. So the box plot is really interesting. You have your median, which is their Q2 or percentile 50. You have the quartile 1, which is percentile 25 or quartile 1. And you have your quartile 3, which is the upper quartile and percentile 25, 75, sorry. You have the upper whisker, and you have the lower whisker, and these are your outliers. These are basically a single data point that are below the lower whisker or further above the upper whisker. Okay, so this is basically a box plot. So if you have, like, glucose levels, you have the median in 104, and you have the quartile 1 being 70, you have quartile 3 being 140, and you have an outlier that will be, like, for example, sorry, this is a quartile 3. This is the upper whisker. And you have an outlier that will be, like, for example, 400, and this patient will be in ketosis probably. So these are basically how we summarize data. Scatter plots are more for when you're actually analyzing two variables, and it actually gives you a visual representation on how well they correlate. For example, if we have LDL, no, total cholesterol levels. This is, I'm sorry. Let me, yeah. We have total cholesterol levels here, and we have LDL levels here. As we all know, they actually correlate. So the more total cholesterol a person has, the LDL will also increase. So they are positive correlated. Okay. So what happens with I don't know, NT-proBNP values here, BNP, and ejection fraction here. When you have a good ejection fraction, like for example 50 or 60 or whatever, your NT-proBNP levels will be low, right? And as your ejection fraction get worse, like for example 20 or 30 or 15 or 8, your NT-proBNP will be increased. So this is a negative correlation. As you can see, the tendency the line of tendency, in the slope, it's pretty much different from positive correlation and negative correlation. And you can actually see it. So that's the beauty of the scatter plots, that it can actually help you understand in a better way what the correlation test, either Spearman or Pearson, is telling you. And we will get to that in a second. And when there's not correlation, basically, I don't know, your age with your IQ. No, probably that is no, that's not correlated because that is adjusted by age. So if there is no correlation, basically the dots will look like this, and they will not follow a tendency. You cannot draw a line here because the line will probably look like this, probably flat, with not a slope like these ones. Okay, so that's it, and we'll end the discussion, I think, of how to describe data. So now we will talk about normal distribution. Normal distribution is basically a representation on how the values of your particular variable in your study population it's doing. Okay, so normal distribution works for quantitative values and quantitative variables. Okay, so you cannot calculate the normal distribution or receive the normal distribution for qualitative variables. Okay, so it only works, or it is only useful to talk about it when we are talking about quantitative variables. So basically, this is based on the laws or the theories that Gauss were, which is a mathematician, was proposing, and he also called a normal distribution bell shape. Why? Because basically the distribution follows the pattern of a bell right here, really nice, you can see. And for normal distribution, it is stated that the mean, the median, and the mode is the same value or around the same value. Like, for example, we have, again, glucose levels, 104. This is my median, this is my mean, and this is my mode. If this is true, then my distribution will have a nice bell shape. Okay, and if we try to calculate the standard deviation, one standard deviation above and below the median, that will encompass 68% of my data. So for example, people with 101 will be here. People with 100 and 100 will be here. People with 99 will be here. People with 88 will be here. Okay, and above the median, the same thing. People with 106, 108, 110 would be above one standard deviation from the median. Okay, and this will be true for the 68% of your data. And two standard deviations away from your mean would be the 90% of your data, and three standard deviations away from your mean will be the 99.7% of your values. Okay, and the rest, like the 0.5% here and 0.5% here, would be basically extreme values that can be outliers. Okay, bimodal distribution is when you have this kind of shape. With, for example, you have a polymorphism in, or the age of onset of Hodgkin lymphoma. It can be bimodal because the most repeated value of age would be, for example, 20, and here it will be, for example, 55. Okay, and this is bimodal because these two values are the mode of this particular value or distribution. Okay, so what happened when the theory that Gauss proposed, that the mean, the median, and the mode is the same, is not true for your particular value. For example, you have NT-proBNP. You can have really high values, like for example in the thousands, and you can have really low values, like for example in 1 or 2 or 3. Okay, so then you will have a positive skew or a negative skew depending on how your values are distributed. For example, when you have a positive skew in your distribution, this is, or a negative skew, this is not normal anymore. The nice bell, like you see here, is not it's not the case. Okay, so you have a skew. It is a skew to one side or another, and this basically tells you that when it's a positive skew, the mode will be first. Like for example, this would be I don't know. Let's talk about NT-proBNP. This will be the mode 7. The median will be around, I don't know, 50, and the mean will be 400. Okay. So this is the reason why when you talk about this is not normal, no normal, this is normal, bell shape, this is no normal when it is skewed. So when this happens, basically the mean is larger than the median and the median is larger than the mode. And when this happens, for example, suppose that you want to summarize this type of variable like NT-proBNP and you want to talk about mean, then your mean will be 400. But this is not in the center of your data. This is not representing the center of your data. It is not what the measures of central tendency are made for, because the mean is no longer in the center, like here. The mean is askew, is positive skew. So this is why when we have non-normal distributed data, we use the median, because the median will always, or in most cases, be in the middle of the data. Okay, so this point is crucial, and I want you guys to have it clear in your head. When you have normal distribution, the center of your data, the mean, the median, and the mode is the same. It's equal. Okay, so you can either talk about mean and median, but most people probably would like to talk about more about the mean, because it is more digestible for some people. Okay, but when you have non-normal distributed data, like for example NT-proBNP, you have to rely on the median. Why? Because the mean is not useful anymore. It is not in the center of your data, nor the mode, but the median is still in the center of your data. Okay? Same thing when you have negative skew. Now, the mean is like something like 4, the median is something like, I don't know, 15, and the mode is something like 80. Okay? When you have these, it's basically the same situation. The mean no longer represents the center of your data, but the median is a better estimate. So this is why when we have non-normally distributed data or values, we use the median and we don't use the mean. Okay? So now I have a question for you, and you can actually reply on the chat box. If we use the median, what will be next to it? The interquartile range or the standard deviation? You can answer in the chat so I can know that you are following the lecture. Okay, IQR. Perfect. Amazing. And if we have normally distributed data, we're talking about means, then what will be next to the mean? Standard deviation or IQR? Standard deviation. Perfect. You have now understand this, and I'm glad. And this is a critical point, because when I was in med school, I didn't understand why in some cases we use the mean and some cases we use the median. And it took me a while to understand this about normal distribution. Okay, so this is perfect. You got it. Great. All right, so now we will go over hypothesis testing. Okay, so basically, all statistical tests try to verify if a null hypothesis is rejected or accepted. Okay, and for example, the statistical tests that you have heard about probably are t-test or chi-square or whatever. Let's do an example with a t-test. So this is based on hypothesis testing. All statistical tests, chi-square, t-test, Mann-Whitney use, Kruskal-Wallis, all are based on hypothesis testing. So basically for these, you have to provide a null hypothesis. And what is your null hypothesis? Most of the time, is something that is a statement that is saying that there is no association between variables, that there is no change among variables, that there is no correlation between variables, that there is no difference, that there is no relationship. That is always the null hypothesis. And this is represented as H0. Okay? The alternative hypothesis, I like to view it as something that you would like to happen as the researcher. For example, I would like to find an association between NT-proBNP and ejection fraction, right? So my null hypothesis will be that there is no association between ejection fraction or no correlation between ejection fraction and NT-proBNP. Null hypothesis, no association, no correlation, okay, no difference. Alternative hypothesis, or also represented as H1, states that there is some difference, that there is some association, that there is a relationship between one risk factor and a disease, for example, okay, or these two quantitative variables, which are ejection fraction and NT-proBNP. So basically, as I like to think about it, null hypothesis is what you don't want to happen as an investigator or researcher, and alternative hypothesis is what you actually want to happen, or the actual hypothesis of your study. Okay, I tend to put it in those terms so that it is easily digestible for people, because sometimes people say like, hey, but I want to prove that there's a relationship between NT-proBNP and ejection fraction. Why my null hypothesis, which is why in what I am basing my hypothesis testing with my experiment correlation test, is testing the null hypothesis if I want to test actually, or I want to prove my alternative hypothesis. So this is why, because hypothesis testing is based on rejecting or accepting the null. Okay, if you reject or accept the null, you automatically reject or accept the alternative hypothesis. Okay, sometimes this is tricky to understand. Sometimes it's kind of the wording is kind of messy, but this is like a good way to understand it. Null hypothesis, no association, no difference, no relationship, no difference. Alternative hypothesis, there is association, there is correlation, there is relationship, or whatever. Okay. So what happened when your null hypothesis is correct, and you actually you use a statistical test, and your statistical test rejects the null hypothesis, or it does not reject it, but it accepts it. So we will get to that now. So in reality, let's suppose that your H1 or alternative hypothesis is true, and your study actually rejects the null hypothesis. If your statistical test rejects H0, which says that there is no difference, then your H1 becomes what you accept as correct, and this is what actually happened. Okay, so basically, if you say like sex actually has an impact or is associated with an increased level of glucose, so males have a higher mean and females have a lower mean. and you do a t-test, and your t-test says, okay, this is significant at 0.005, which is lower than 0.05, and this is significant, you reject your null hypothesis and you accept your alternative. But your alternative is true, so congrats. This is the correct result. This is also what is called power. So power is the probability that you actually reject the null when the null is actually true in reality. So this is power. What happened when you do the same analysis? You do a t-test with female and males, and you want to know if females has a higher value of glucose. Well, what happened in those cases, and let's suppose that the study does not reject the null hypothesis. It says, okay, you have like, I don't know, 30 participants and your p-value is 0.6. In this case, this is not a significant result, and you cannot reject the H0, which is your null, and your H0 is supposed to be true. But in reality, we know that H1 is true. So you incur in the type 2 error, also called beta. Okay? So beta is basically the probability to fail to reject the null you were supposed to reject it, but you actually accepted because your p-value was not significant. And in reality, the alternative was the correct one or the true. Okay, so this is type 2 error, also called beta. All right, so let's go into the other aspects of this chart. So what happens when you have a hypothesis testing and your study rejects the null hypothesis? It says, okay, there's actually a difference between females and males in terms of glucose levels, and your p-value is 0.001, and you reject the null hypothesis, but in reality, the null hypothesis was a true one. Well, this is the alpha, also called the type 1 error. Okay, so the type 1 error is the probability that you reject the null, but the null was actually true. So you incur an error, and that's called the alpha. And what happened when you have the opposite, and your study is not significant? You fail to reject the null hypothesis, but the null was actually true. Okay, so that's a correct result. Okay, that's not an error. That's what you were supposed to do. Okay, so when people talk about sampling and sample and population, it's basically it is noted that you will be talking about power and also alpha probability. So you want to account your alpha to be as low as 5%, and you want to have your power, or the probability that your study rejects your null hypothesis when the null is true. When the alternative is true. So when you're doing sample size calculations, you actually want your power to be you actually want your power to be as high as 80%, and this is by convention. And your alpha, which is this one, you want to be it at fixed at 5%, because you want that your sample size actually has a good chance, which is 80%, which is not bad, to capture that you fail to reject the null and the alternative is true, which is what happens, which is reality, which is the correct result. And you also want a low probability that your study rejects the null when the null was true. Okay, so that's the relationship between power, type 1 error or alpha, and sample size, just in a glance. I don't want to get too caught up in that. But let me know if you understood these concepts. These are little complex, not that easy to digest, but I think that if you think of it in that way, you can actually understand how the hypothesis testing and the statistical tests are you know are conducting or performed. Hey, Rahul.
Dr. Mautong, this was a fantastic lecture. Let's do the part two of this lecture next week, and then we hope that our scholars and then the people who are listening to these lectures, they are getting benefit from it. So thank you so much.
Yeah, absolutely. It was a pleasure. So if anyone has a question that I can resolve, I will be thrilled to do it. So this is the time, guys.